Hi everyone, welcome to this video on quantum mechanics. In this video we'll be covering the basics of quantum numbers and how they are used to describe the behavior of electrons in atoms. To start, let's first understand what we mean by the term quantum. In physics, a quantum refers to the smallest unit of a certain physical property. In the case of electrons and atoms, we use quantum numbers to describe various properties of the electrons, such as their energy levels, spatial distribution, and intrinsic spin. Before we go to the quantum numbers, let's the origin and experimentation which led to the improvement in this field. The origin of quantum mechanics. Quantum mechanics began in the early 20th century with the discovery of the photon, or light particle. Scientists like Max Planck and Albert Einstein were trying to understand the behavior of light and how it interacted with matter. They found that light behaved in ways that could not be explained by classical physics, and that it could exist in both particle and wave-like forms. This led to the development of quantum mechanics, which is a branch of physics that explains the behavior of matter and energy on the atomic and subatomic level. The double-slit experiment. One of the most famous experiments in quantum mechanics is the double-slit experiment. It illustrates one of the most mind-blowing phenomena of quantum mechanics, wave-particle duality. In this experiment, a beam of particles, such as electrons, is fired at a screen with two slits in it. On the other side of the screen, a detector is placed to measure the location of the particles. When the experiment is conducted, we see that the particles create an interference pattern on the detector, which is something that we only expect to see with waves, not particles. This means that particles can behave like waves and vice versa. This is known as wave-particle duality and is a fundamental concept of quantum mechanics. Quantum entanglement. Another mind-blowing phenomenon of quantum mechanics is quantum entanglement. This occurs when two particles become correlated in such a way that the state of one particle can instantaneously affect the state of the other, regardless of the distance between them. This means that if two particles are entangled, and we measure one of them, the state of the other particle will change instantly, even if it is on the other side of the universe. Einstein referred to this as spooky action at a distance. Now let's about quantum numbers. There are four types of quantum numbers: the principal quantum number, n, the angular momentum quantum number, L, the magnetic quantum number, m_L, and the spin quantum number, m_S. The principal quantum number, n, describes the energy level of the electron, with larger values of n corresponding to higher energy levels. It also determines the size of the atom's electron cloud. The angular momentum quantum number, L, describes the shape of the electron's orbit. It can take on integer values from 0 to n1. It means that for n equals 1, only L equals 0 is possible. For n equals 2, L can be 0 or 1, and so on. The magnetic quantum number, m_L, describes the orientation of the electron's orbit in space. It can take on integer values from L to plus L. The spin quantum number, m_S, describes the intrinsic spin of the electron, which can be either up or down. It's important to note that each electron in an atom is unique and it is described by a set of four quantum numbers which can be written as n, L, m_L, m_S. These quantum numbers are also the solution to the Schrödinger equation, which is the basic equation of quantum mechanics. So, to summarize, quantum numbers are a way to describe the behavior of electrons in atoms by specifying their energy levels, spatial distribution, and intrinsic spin. By understanding quantum numbers, we can better understand the behavior of atoms and molecules, which is essential for understanding many areas of physics, chemistry, and materials science. Now let's see some examples of quantum mechanics usage in real life. Quantum computing. Quantum mechanics also has practical applications in the field of computing. Quantum computers use the principles of quantum mechanics to perform certain types of calculations much faster than traditional computers. This is because quantum computers can exist in multiple states simultaneously, allowing them to perform multiple calculations at the same time. Quantum superposition. Another fundamental concept of quantum mechanics is superposition. This principle states that a quantum system can exist in multiple states simultaneously, meaning that a single particle can exist in multiple positions at the same time, or that a single photon can have multiple polarizations. This phenomenon is what allows quantum computers to perform multiple calculations simultaneously. Quantum tunneling. Another interesting phenomenon of quantum mechanics is quantum tunneling. This occurs when a particle, such as an electron, is able to pass through a potential barrier that it would not be able to pass through if it were behaving according to classical physics. This is because, according to quantum mechanics, a particle can exist in multiple states simultaneously, and therefore can have a small probability of being on the other side of the barrier. Quantum decoherence. One of the biggest challenges of quantum mechanics is understanding how the quantum world interacts with the macroscopic world we see around us. One theory that helps explain this is the concept of quantum decoherence. This occurs when a quantum system loses its quantum properties due to interactions with its environment. Essentially, this means that quantum systems can quickly lose their quantum behavior when they come into contact with their surroundings. Real-world applications. While quantum mechanics may seem like a purely theoretical field, it has a wide range of practical applications. Some of the most well-known include quantum cryptography, which is used to create unbreakable encryption methods. Quantum computing, which can be used to perform complex calculations much faster than traditional computers. Quantum simulators can be used to simulate complex systems such as those found in chemistry and materials science. Conclusion. In conclusion, quantum mechanics is a fascinating and endlessly complex field that has revolutionized our understanding of the world around us. From the origins of the field to its mind-blowing phenomena and real-world applications, quantum mechanics continues to inspire new research and discoveries. While it can be challenging to wrap our heads around some of the concepts, the more we learn about the quantum world, the more we come to realize just how little we actually know. Thanks for watching. I hope this video helped you understand the basics of quantum numbers and widen your view on quantum mechanics. If you have any questions or comments, feel free to leave them in the comments section below.